Welcome. So I will show you some practical application of optimization, yeah, in engineering. And engineers, we love optimization because usually we have a design, for example, that we want to optimize or something like this. So I will show you like two examples where we use this optimization method. I will show you like one remediation example where we use and optimize. In this example, I will show you like how to develop like the objective function for a real world problem. And then in a second, I will show you like a second application that is like how to use optimization to calibrate a model, flow model, like groundwater flow model. And I will show you the comparison between these methods that we learned here, like this derivative-based method and the heuristic method and the stochastic method. Yeah, an interesting stochastic method. I mean, okay, so we will just basically explore engineering application of optimization. Uh, so this is a groundwater remediation of a petrochemical site. So this petrochemical site is somewhere in Italy. Oops, is somewhere in Italy. The Mediterranean Sea would be like somewhere here you have this petrochemical site, and it seems that there were like some leakage which led to groundwater contamination. So the objective here is that we want to design something called pump and treat. Pump and treat systems, that's where you pump the water out and then you treat it before you discharge it. And the reason why we want to design this pump and treat system because we want to contain the plume, the contaminant plume within our site. Like we don't want this plume to go and contaminate like this neighboring site. And for example, this could be like serious issue because you see a lot of agricultural land here, and if they are using this water for irrigation, that is not going to be good because I will show you like how this water is really badly contaminated as I will show you in the next slide. So as you see here in the next slide, we like identified like two types of contaminant plume. One is chlorinated hydrocarbon, like these guys, and one is like PTEX. PTEX, that's like benzene, toluene, and xylene. Yeah, so that is what were identified, and basically, so we these were available at like a very high concentration. And what we did, we just like delineated like two plumes here. So this dark gray, that would be the PTEX plume, and the light gray, that would be the chlorinated hydrocarbon. We just delineated this with particle, and I will show you in a minute why like we delineated this was particle. Like the reason we delineated this was particle because we want to design a pump and treat system. Uh, in this pump and treat system, we want to capture all these particles, but we want to capture this particle separately. So we want to capture this chlorinated hydrocarbon plume separately and this PTEX plume separately, because our hypothesis is if you can capture these two plumes separately and treat them separately, that will save some of your design costs. That is like our hypothesis, yeah. But before we capture this plume, we need first to develop like a flow model, like a groundwater flow model. So you again, this is not a hydrology class, so I will just not say like a lot of these detail, like how to develop like this groundwater flow model. But basically, like we developed actually like four different conceptual model, and we calibrated. So these are some of the parameters that we use, like how like these model differ for one another. This is like our calibration parameters. So for model one, we use hydraulic conductivity. For this, we use like recharge rate and so on and so forth. And see, these four model were calibrated fine. So the normalized root mean square error for the calibration is, I mean, for this one, less than 10%, here is less than 15%. Model calibration means that I want my model, like for this model to be reliable and I can use it, it should be able to reproduce what I'm observing in the field. So model calibration is, so I get some data from the field, let's say hydraulic head, and my model is simulating hydraulic head, and I want these two to match. So how can I make these two match? I keep playing with the model parameter until I get a good fit between what I am observing in the field, like my state variable, which is like hydraulic head, and what my model is measuring. Yeah, but again, this is not a groundwater hydrology class, or this is, and this detail, like you will learn them, and you will learn how to calibrate, like collect data, calibrate the models, that's like in other classes, not in this one. Okay, so here, this is, for example, an example of one of the calibrated models. This is my hydraulic conductivity field. These are different hydraulic conductivity values. So we calibrated this model. These are like my boundary condition. We calibrated this model, and then we have 4 mud flow models that are calibrated. Yeah. So these models can now simulate the flow, like the flow in the site. So my site is here, and it's a model domain in general. Yeah. Again, we have like these two type of contaminant. One, so this like dichloroethane, for example, that's like a low absorption and low air partitioning coefficient, so we cannot like do an in situ treatment. So our idea was like, this is like the contaminant water from joint plume capture. Like if we captured everything and we mix them, then the mixed water will go to a catalysis unit, for example, that is to treat the chlorinated hydrocarbon, and then whatever is remaining will go through a granular activated carbon unit that will be to treat the PTAX, yeah, and then the treated water will be with allowable concentration will be discharged. That is like business as usual, but our idea was like, now if we could this contaminated the chlorinated hydrocarbon, we capture it separately and we treat it through this CAT unit, and the PTEX hydrocarbon we directly treat it with the granular activated carbon, and then this will save some cost. So we our hypothesis that this one will save some cost versus this one. Okay, so how to do this? So to do this, as I mentioned, we delineated like, so this our concentration, we delineated them by this particle, and our objective here, what is now we will get to the optimization part. This is where I'm getting to. So previously this was some just hydrology, just to set the context for this optimization problem. But now, so you see here, like you see this area, I'm like just exaggerating like our side boundary here. So what we want to do, this is my plume. First, we don't want this plume to go outside this side boundary, because if they went outside this side boundary, they will contaminate like the adjacent area, which we don't want. Second objective. So first objective in my, like, remember when we were setting the objective function, it has like several objectives. So my one of these objectives is that I want all these particle to be contained within my site. That's my first objective. Second objective, I want to capture like these guys separately and like these guys separately. I don't want any cross contamination, because if I capture them separately, I could treat them separately, each one with its optimum like treatment technology, and that will save the cost. So how do we do this? We do this with actually optimization. So basically what we want to do, we can put like pumping well here. So I can put like, let's say a pumping well here, 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 a pumping well here. And this guy might like capture like maybe these guys here. This guy might capture like these guys here. This guy might capture like these guys here. Oh, you see, this guy will capture some of these guy and some of this guy, so cross contamination. So this guy, the location of this guy is not good. So maybe we need to move them to a little bit here, yeah. And this guy might also do some cross contamination, so you move them here. But this guy, like how it will capture does not only depend on its location, but its pumping rate. So if I have like a bigger pumping, then I will capture like more guys, yeah, versus if I have like smaller pumping. So let's say like this big circle is like 100 meter cube per day. This small circle is like 10 meter cube per second or day, or yeah, per like second, yeah, whatever, yeah. Uh, then this guy, like the small one, will only capture here versus like the big. If I have big pumping, this will be captured here. So the problem is it's not that I am only uncertain about like the how much do I need to capture, like this much, that much, or that much, like pumping rate, but where to put these guys, like to put it here, put it here, put it here. So this is exactly the optimization problem. So that's what the optimization will do. All the previous examples that we solved with the optimization, we just have one independent variable. So for example, like these costs that we were doing, the dependent variable was the cost, the independent variable was the length or the width or something like this. Here in that case, we have like, we will assume like 9 pumping well, and each pumping well will have like 3 decision variable, like its location, its x location, so here, and its y location, like, so that's the x location, should it be here, should it be here, should it be here, and then its y location, should it be here, should it be here, should it be here. And then that is like the first two, like, so the first decision variable is like x, the second decision variable is y, the third decision variable is q, how much? And then I have like 9 of these guys. So how many decision variable I have? I have 27 decision variable. In optimization terminology, this is called like a 27 dimension problem. Like, remember all these previous examples that I showed you previously, I could draw it on like a 1dx, and I will say, okay, this is my objective function, this is my x, this is my f of x. In this problem, I have like f of x1 to f of x. 27, so it's like 27 dimension problem, yeah. And this is like my f of x. So my f of x here, what would be my f of x here? That would be like the objective function that I will be formulating. So this is the objective function, and these are my decision variables. So my decision variable, again, like for each pumping well, like where it is located, x, y, and how much do I need to pump, like the q. Yeah. So, okay, now, but this objective function would be not easy, because like, what is this objective function? Like, first of all, I want to minimize q, like how much I'm pumping, because like the more I pump, the less cost, like the more cost, like more energy cost and so on, and even treatment cost, because you get more contaminated water. So I want to minimize q. That's like my objective functions. That's like what I want to minimize, subject to what? Subject to several constraints. Subject to number one, I want to disjoint capture. So subject to this joint capture. Subject to what? Subject to that I want all particle like within site. Subject to what? Subject to that I don't like, see, this is my model domain, this is my site domain. I don't want the pumping well to be here or here or here or here or here. I want all my 9 pumping well to be inside my site boundary. Because this is not, we don't like, this is other people, not the land of this, like belong to this property. So subject to like or pumping well within, so here, or like plume within site, and here's a pumping well within site. Oh, so I want to minimize Q subject to this, like I want to capture this guy separately and this guy separately, like these two guys separately. I want all my particle to be contained within like this site boundary here. Yeah. And I want all my pumping well to be contained within my site boundary here. I think that's it. Yeah. That is it. So now, how could I formulate like this objective function? Like, how could I formulate like this objective function? How could I formulate this? So that is basically what I'll be showing. Let me show you like some solution. Yeah, let me show you some solution. So here, this is like a solution. Actually, this is a successful solution, because like you see this solution, again, why do we have 4 solution? Because remember, we have 4 model. We don't only have one model, like because like we don't know reality. So what you generally do, you can create different conceptual model, you can calibrate them, and then you run your optimization, because you don't want to risk doing is design, which is very expensive, like 3 or 4 million euros. This design is based on just one model, one conceptualization of reality. So we create like 4 different conceptualization. All of them are well calibrated. As you saw the calibration result, all of them can simulate like external reality well. Here, this is the pumping rate, like meter cube per day. So like the small guys here, for example, that would be like 10 meter cube per day. The big guys like this guy here, that would be like 100 meter cube per day. That would be like 100 meter cube per day. So so like this particular solution, this is where the line pumping well, like each location and pumping rate is proposed. So this is like you keep running your models, and you run your model, and then basically like you put this pumping well, you put it in your model. All this happen in the patch mode. So basically like you need to use a programming language to do this. So basically like you you propose like a design, you write it in your model, you run your model, and then you evaluate your objective function until you find like the minimum values that you're looking for. So this solution basically succeeded, because you see here, this is captured separately than this guy. All the pumping well, like the 9 of them, are within the side boundary, and the plume is almost contained. Like you have something here, you have something here, but most of it is mostly contained within the side boundary, which means that actually our optimization work, our objective function is working, because we got what exactly we need. So basically, I mean, this is just like to show you like the remaining steps. So after you have a design, like what do? Like you create another model. This is called like a contaminant transport model, and we use something called like MT3DMS, and this will simulate the transport of like your different contaminants. And like any engineering design will have like a 30 years period. That's like how we make any designs. And after you get your contaminant load, you design like your contaminant system, like your CAT unit and your granular activated carbon unit. So you design like these two systems, and then you do a cost analysis. Basically, like you do like what do you call this? Like engineering economy. Like you use like you get like the net present value for like this like a 30-year design, basically, yeah, using engineering analysis method. And let me just show you, like in case you are curious about like our final solution. So this is the traditional thing, like disjoint capture, and this is, sorry, this is the disjoint capture, like our innovative method, like where you can capture these things separately, and this is the traditional thing. See, you see, for the disjoint capture, the queue, you need to pump more, because you are trying to do something more difficult. You are trying to capture these things separately, so you get like your pumping rate. So here we run the optimization several times, and that's why you get like this, not just one solution, but multiple solutions. That's how you account for uncertainty also. But for the disjoint capture, if you are capturing everything together, you don't need to pump much, so you can uh, pump less. But the cost, you save here much cost. So the cost of this guy is about like less than 3.5 million euro, and the cost of this guy is more than 3.5 million euro. So basically, with that's like, so that's like 3.2 versus 3.9. So basically, like with this joint capture, like with this, like by using this optimization method to do this joint capture, you need optimization method, by the way, for both of them, for either joint or disjoint, because you also need to, as I mentioned, to keep this guy inside, you need to find their location and pumping rate. But you see, this method, you were able to save some money. Yeah. Here, this is like an example, like this is what I want to show you. So here, this is an example when you don't build this, like here, this joint capture. When you don't build it in your objective functions, then you get something like this, yeah? You get cross contamination. You are not jointly capturing them. Now, when you don't build that containing the plume, like plume containing plume within site. When you don't build this in your objective function, when you don't build this in your objective function, then you can get like, like the plume can be escaped. Because again, I mean, if you didn't build it in your objective function, your optimization will not do it for you. You need to build it in your objective function, yeah, for your optimization to work, yeah. Then you get like this contamination. Here you are also getting it. So here this does not have the joint capture and does not have plume within site. If you build like these two, then you get exactly what you need. So you see here's this particular solution. These two are captured separately and the plume is perfectly contained within the site. So now this is my question, like how could you build this into your objective function? So let me just show you like how we did this. So here, I don't know, can I make this maybe like this? Yeah. Okay, so this is, let me show you like how we did this. This is like my objective function here. Basically, what this is telling you is like I need the minimum value of f giving q, which is a function of x and y. Because, okay, so how could I build this objective function? So here, uh, okay, this is like where this is the penalty function. So basically, like I build like this objective function through like penalty. So basically, I will tell him this uh, if the pumping well is outside, like the plume, give a big penalty. If the plume is outside the side boundary, give a big penalty. If Q is large, give a big penalty. So basically, that is like how you build this within the objective function. So my objective function is like the sum of Q time my penalty. So this is like q as a function of x and y time my penalty. And how do I do this like penalty function? So penalty here, this is like weighting factor, and this r is like the ratio, for example, of the particle, yeah, of particle captured by the well to the ratio that are, so basically this is for cross contamination. So basically here, if I have like cross contamination, then through knowing the ratio of the particle, like which type of particle captured by which well, or like this actually to capture. Oh, one objective I forgot to tell you, we need to capture all the particles. So if one of the particles not captured, then you give it a penalty. Yeah. So like we go down here. What is the second? Like ensuring the placement within the accessible placement area, like ensuring that all the well are within the placement area. So again, so this is my previous penalty. Then I add like this additional weighting factor here. So I give like if it's outside, then you give it like additional penalty. Then what is the third thing? Containing the capture zone within like the given area. So I want, remember all like this capture zone to be within the same area. How can we do this? Basically, we calculate the travel time in the site and travel time outside the site, and to keep, and what we want to do, we want to keep the travel time outside the site almost close to zero. And that's how you can ensure that everything is captured within your uh, site. So you do this like travel time ratio, and then you build it into your penalty function here. What else do I want? And then finally, I want to have this disjoint capture. So I have like this 5 constraints. So like I want to have this disjoint capture, and this basically you have this, you define this cross contamination parameter. Basically, like each plume will have like an index, and I want like this pumping well to capture just one index, not two indexes. Yeah. And if it has like more like a mixture of indices, then you give like it gets a penalty. Yeah. And then you put all you build all this basically. That's like, so that all would be your penalty function. You put it here. So basically that is the, in real life, this is the function that I want to minimize. So I want to minimize like this guy, uh, given like, and this is how I built like all like subject to this, subject to this, subject to this, subject to this. And this guy, like, unlike the simple problems that we solve that has only one dimension, this guy has 27 dimension because I have 9 pumping well. Each pumping well have an X. Let me make this bigger, like here. Each pumping well has an X, has a Y, and has Q. Yeah. And that is basically like how we did it. And then that is like how you do this in real life. But again, this is just like beyond the scope of this course. All I just wanted to show you like in this course is like this simple problem so that you understand like simple like some terminology like local minimum, global minimum, local maximum, global maximum. So here, this is a minimization problem. The objective of the optimization algorithm is to reach the global minimum solution or near global minimum solution. That is where you will ensure that you have the minimum pumping rate while satisfying all these additional constraints that you are putting on your optimization problem. And I'm just looking how we are doing in time. We're still doing good in time. We still have about 20 more minutes to go to keep it less than 2.5 hours. Okay. Basically, that is you can solve this with a derivative-based method. In that case, the derivative-based method, remember, like I cannot even plot the objective function here because that's like 27 dimensions. So I cannot plot it. But if I plotted this objective function, it might not be smooth. It could be, it is not discontinuous. You will not have any discontinuity. You might have some sharp edges or you might not. So in that case, like you can solve it with derivative-based method, but it might not. The advantage of this derivative-based method, it will be much faster. Like the number of function evaluation to find the final solution might be like 10 or 15 versus like the stochastic method, which we solve it here, is you maybe need to run for like hundreds of time, not just like the tens of time, but hundreds of time. But interestingly, like this stochastic method that we solve it here is also based on gradients. So it calculates gradients, but it does not calculate gradients using derivative. It calculates gradients using other methods, like it calculates gradients stochastically. Okay. So that is the method that we used here. Yeah. It's called like covariance matrix adaptation. Yeah. Okay. So this is one application. Let me show you like another application. Basically, in this application, the objective was to see like how to build like this objective function. Yeah. Let me show you like another application for optimization that would be like model calibration. Let's do this one. So here, for example, like we have like a model and we want to calibrate this model. And let me show you what do we mean by model. Okay, I don't have a table for the model parameters. Okay, do we have a table for the model? Yeah, here we go. Okay, so each model have like certain parameter like hydraulic conductivity, specific storage, anisotropy, some conductance of two false boundary condition, and we want to keep like tuning these parameters. That's like model calculation. Keep like playing with these parameter until we get the best match between what our model is simulating and what we are observing in the field. So for example, the hydraulic conductivity, we believe that for this guy, it ranges from 15 to 35 meter per day. Remember? Does this ring a bell? Let me show you here. Remember, like in these problems, we define like a range. So this is like my x1. It goes from -2 to 3, for example. That is exactly the same we are defining here. Like this goes from 15 to 35. But in this problem, or like these type of problems, this only has one dimension, like x1. But here, this problem has 5 dimensions. It has like x1, x2, x3, x4, and like this guy here, yeah, x5. So for each one, like you define like a range, and this is the optimal solution. Like this is like you want to find like the parameter value that will minimize the error. Like the error would be the difference between what your model is simulating and what you are observing in the field. So your optimization will basically like find these values for you. All of them fall within our range, like nothing really outside the bound, like at the endpoints. So all these are like local solution, or hopefully like a local minimum, or hopefully a global minimum. Because sometimes, especially derivative based methods, they can just like numerical methods, they can get stuck in a local point and then don't leave it, like when you're solving these numerically. Yeah. Okay, so basically that is how to do it. We tried this on a simple problem. So here, this is a simple problem. This has 81 variable. Like we are trying to estimate the hydraulic conductivity in each of these cells. This is the true solution. So this is like the true solution. This is like the optimal, like this is like, so we know the real model, we hide it, and we design an optimization problem, and we put them in a race. Like we put several optimization algorithm in a race and see which one will get like this true solution. So, I mean, I will not go into the details, but I just want to show you these guys. I think this is called like differential evolution. This is called like genetic algorithms. This is called like ant colony. This is called like particle swamp. And this is like the covariance matrix, the ones that I showed you early. And this is what? This is a derivative based method. Like Levenberg-Marquardt, this is by calculating derivative same to what we learned in this lesson. Like which one? So again, this is the true solution. Like the optimization does not know this, but we know this. We know that this is the true solution. And here you see like this one, the covariance matrix adaptation almost got the true solution. But you see the derivative-based method, not bad at all. It knows that this is a step function, like this is something here and something here. So it knows something here. It failed at the boundary because of some noise, but overall, I think like these two, like the derivative-based one and this one, like got like very, like this is almost like a near global solution. Yeah. This one got like stuck maybe at like some local optimum or something. The advantage of this one is that you can get like to almost like a near global solution, as you see here. The advantage of the derivative based one is that they are quick. So here I need to estimate my functions, I don't know, like thousands of time. Here I need to estimate it like tens of time. And sometimes each function evaluation will be like a one model run. And sometimes these model runs will take like a day to run. Yeah. So you don't want, if it take days and you run it like 10,000 times, you don't want to do this. I mean, we do this, but we do it on high performance computing. Yeah. But so if you want to get like a more accurate, like a more precise or solution, you can use this guy. If you want to, if you have like a complicated problem like this one, if you use derivative base, you will get not bad, but it will not be as accurate as this guy. Yeah. Basically, this one shows you the solution progress. So like this is the first iteration, that's what the optimization know. And then as the optimization learn, it now started to know like after. So at iteration 1, that's the initial solution. At iteration 400, it realizes that you have this step function. At iteration 800, see now it's starting to get rid of this noise here. And at iteration 1000, you got something almost true solution. And then here I kept like you kept running it for 4,000 iterations. The solution does not improve much. Basically, like that's like your variance here is improving, but like the solution itself is not. Okay, so I just like give you like a quick flavor of optimization method. Again, no hydrology, because like if you want, for example, to know how to set up like one of these model and how to use like this particle tracking, for example, you take groundwater hydrology. Groundwater hydrology, like you will learn the basic concept of groundwater hydrology, then you will learn how to get field data, create a conceptual model, set up a numerical model like with one Mudflow, and then I think in your term project you will do a problem like this with particle tracking and design like a capture zone for a pumping well or something like this. But in this course, we mainly focus on just basic concept, not hands-on experience on practical application. Okay, so that is the main idea of this course. Okay, so I don't want to keep this like long. It's already like 40 minutes, so I will stop here. See you in the next video.